So, hello. Okay, we are going. So the component of the UV visible spectrophotometers, they are very similar. Similar. We know that is the sources of what? Sources of UV visible radiation. Now monochromator, sample containers, and the detectors. So these are very simple instrument it is, and we are going to discuss all these components one by one. Okay, number one, that is sources. So this is the block diagram. That is light source is there, chromator, monochromator, then it is the incident light, that is P naught, power is 0, that is incident light, that is maximum power. Then it is passing through the sample. So now this radiation is being bombarded on this sample, having a path length of what? B. That is what? That is the greater the and greater will be the absorbance and so on and so forth. After passing this radiation from the sample, some unused radiation will be coming out of the sample, and that will be detector going to the detector, and where it is combined, how much is being unused. So if, for example, this was 100 unit, this was, for example, say 65, so it means 35 have been used by the interaction with this sample. So by radiation, after in and out, the P naught and P, we are able to calculate how much how absorbed by the sample. Now this P naught is the power of the incident light, whereas the P is the transmitted light from the sample, and B is the path length, nothing else. Now, for example, if we are passing the radiation into this sample, it is the I, that is the IT, that is the P. This is P naught, and this is the length, that is the path length through which the sample is present. So this is the path length. This is generally 1 centimeter. Okay. Now there is Lambert law. This is theoretical. There are two different laws. This is Beer and Lambert. These are two different scientists. They put forward the law at the same time, almost simultaneously. They proposed these laws, and Lambert said that the absorbance of a material sample is directly proportional to its thickness. Greater is the path length, greater is the absorption. So the absorption of a light is directly proportional to the path length of the cell. Whereas Beer says that The absorbance of the electromagnetic radiation is directly proportional to the concentration of the absorbing species in the material sample. Absorbing species, for example, if it is a copper solution, so copper is the analyte, is the absorbing, as the water is this other material in which the copper is present. So it depends upon the concentration of copper in the solution, whether it is polar, it will be absorbing lesser as compared to 2 molar copper solution. So 2 molar copper solution will be having higher absorption value to 1 molar absorption solution. So by mixing these two laws, Beer and Lambert, we have a Beer-Lambert law, or simply we say that the Beer's law. So this laws, their assumptions are: this law is obey. This will be obeying that the light, when shined on the sample, must be have a one wavelength. That it should be a monochromatic. Chromatic light must be there. This Bayes' law holds good when we are using monochromatic light. That is the wavelength, the light of one wavelength only. The other thing is that it can hold good. It will obey. This Bayes law obeys very good response when the analyte must not participate in the concentration dependent equilibrium. There should be no change in the concentration. There should be no change in the concentration during the measurement. And this is for simplicity, we can have an example of the weak electrolytes such as acetic acid. This technique is good only for, is not good for weak acid such as acetic acid. Now, you know that acetic acid is a weak acid, and when it is being dissociated into the acetate and the proton, it recombines it. It recombines acetate and the proton, they recombine to form acetic acid. So if there is something like that, the association and dissociation is taking place. So it will have a different absorbance. Acetate will have a different absorbance as compared to acetic acid. Similarly, proton has different absorption as compared to the acetic acid. So if there is they are in is they are not in equilibrium form, they are dissociating and associating. So there is a dynamic equilibrium. So if they are not in the dynamic equilibrium, though probably it will be not working. And the third point is that the solution, the analyte must be a dilute one. It should be analyte concentration should be a smaller one. At higher concentration, it will be not working. So, that is the Beer-Lambert law, or simply Beer law. The rate of the decrease in the intensity of the monochromatic to the thickness of the medium as well as the concentration of the absorption substance. So that absorbing I naught over I is the I naught is the initial intensity of the light, and I is the transmitted light from the sample that is proportional to the length as well as the concentration. This length, this is the proportionality constant. This is known as epsilon, and this epsilon is also known as molar extinction coefficient. It is also known as molar absorption coefficient. It is also known as molar absorption. So this absorbance that is equal to I naught log I naught over I, that is equal to LC, or it is this if this is equal to A, that is the absorbance A, so that this equation is simplified as A is equal to epsilon LC. This is the epsilon coefficient, molar extinction coefficient. or molar absorptivity, L in centimeter, and C is the concentration, that is always in mole per liter. Okay, so this epsilon, that is the molar extinction coefficient, can be defined as the absorbance of a solution of concentration 1 mole per decimeter cube and a path length of 1 centimeter. So we can measure the epsilon value with known concentration and the known absorbance and the path length. We can calculate the epsilon value, and this is characteristic. This characteristic, this will be different for copper. It will be different for iron. It will be different for cobalt. It will be different for benzene. It will be different for ether. It will be different for. So it is a characteristic term. So this is the Lambert-Beer law, so or simply Beer law, that is A is equal to epsilon LC. Very simple one. More few words. The epsilon A is equal to epsilon LC, where A is the absorbance, epsilon it is the Greek letter, the L is the path, and C is the concentration. So molar, this is the epsilon is the molar coefficient. So this is very simple Beer-Lambert law, or simply Beer law. Again, this, oh, it is repeated. Sorry for that. Now, absorbance, we can have a relation with the absorbance and the transmitters. Now, absorbance, mathematically, absorbance is equal to I naught over IT, or transmitted light, or it is if it is transmittance, it means that A absorbance is equal to minus log base 10 of transmittance. In that, if we have a transmittance value, we can convert it into the absorbance value. If we have an absorbance value, we can convert it into transmittance. Okay. Now, absorbance is equal to log I naught over IT, that is equal to epsilon lambda. Epsilon means, lambda means that this is the epsilon, this is the absorptivity at the wavelength which is have a maximum absorption, lambda max. So multiplied by length of the cell, and that is the concentration. So this is an epsilon LC, or simply epsilon LC. Okay. Now this is again the repeated one. Okay. When we are measuring the absorbance value, we know the concentration. We in a given set of example, in a given set of instrumentation, L is the constant, that is we are using the same cell repeatedly. Epsilon is the constant for a specific, for example, copper, nickel, cobalt, it is a constant. When we are measuring, for example, cobalt, its epsilon value is constant, L is the constant, that is the cell wavelength, cell is constant, and only the absorbance is directly proportional to concentration. If we change the concentration, we will be having increased. So if we make a standard solution for 1 ppm, 2 ppm, 5 ppm, 10 ppm, we calculate the we measure the absorbance, we can have an idea that we can make a correlation curve like that. This is the absorbance value. This is the concentration. This is, for example, micromolar or ppm, whatsoever units you are measuring. But these are the standard solutions. We are measuring the solution, and this is the standard 1, standard 2, 3, 4, 5. This is the absorbance values against them, and then we are plotting it, make absorbance versus what concentration we are getting is. And this is the linear one. It means as we increase the absorbance, as we increase the concentration, the absorbance is increasing in a regular way, in a linear way, we will say we will say that this is the linear calibration curve. Okay. Now, there could be certain situation. This curve is, although we are measuring the concentration, increasing the concentration, this is the absorbance value whatsoever. So it is not a straight line like this. It is curved one, and this curvature is toward the x-axis, toward the concentration axis. So although it is increasing, but not to a sufficient way, it is not a linear, it is not increasing linear. So it means that we have only up to this much point we have a linear relation. After that, toward the concentration axis. So such type of the curve, they are called as non-linear calibration curve. Again, few words about transmittance. It is the reverse of that, but that is the absorbance. But it is defined as the ratio of the electromagnetic radiation leaving the sample, Pt, to that of the incident on the sample, that is P0. Remember, when we say we have a absorbance value, that is, for example, this is the lamp. It is giving us radiation P0, original P0, the initial concentration, radiant power. This is the sample, and then it is emitting sample. That is, it is always lesser than that of the P0. So this is transmitted, how much is being transmitted from the sample. So that is the ratio. That is called a transmittance. That is transmittance equal to Pt, transmitted radiation, divided by the initial radiation. And if we multiplied it by 100, we can say that this is the percentage transmittance. So multiplying the transmittance by 100, we can have a percentage transmittance. That is percentage transmittance equal to T multiplied by 100, or Pt over P into 100. That is the percentage transmittance. It means that it varies. This value, percentage values, varies 0 to 100%. When it is 0% transmittance, it means everything is being absorbed. If it is 100% a percentage transmittance, it means nothing has been absorbed. Okay. We have a relationship with, again, absorbance and the transmittance. Absorbance is equal to minus log of T. It is minus log of T. Minus log of T means TPT, or if we change the sign, we will have a log of P0 over, and that is what? That is the absorbance. It is the reverse of that. Okay. This is a very simple equation and very important equation. Now, if we have a we can convert it into the absorbance with the help of very simple equation, that is absorbance equal to 2 minus log of percentage transmittance. This is very simple equation. Now, for example, convert 56% transmittance to absorbance. So we are going to measure the absorbance, and that is 2 minus log of percentage, 2 minus log of 56, that is the absorbance. Okay. Now 56, this is the absorbance percentage transmittance, that is equal to 0.252 absorbance. So this is the absorbance only. Now, conversion of the value from the absorbance to percentage. If we have a percentage absorbance, we have the absorbance, we can transmit it percentage transmittance, and that is percentage transmittance is equal to anti-log of 2 minus absorbance. Okay. Now convert the absorbance of 0.505 transmittance. So when we put this value in here, so it means That is percentage anti-log of 2 minus 0.505, that is equal to 31.3% transmittance. So by this simple equation, able to calculate, we can transform. If we have a transmittance value, we can measure it the absorbance. Absorbance value, we can calculate the percentage transmittance from this simple equation. Okay. Coming to the instrumentation sources, monochromator, sample container, detector, and the monochromator, for example. We are using generally quartz, prism, and gratings. Prism and the gratings. These are made of what? Quartz. Detector, we are using photomultiply tube. The block diagram of this is the light source. That is the second component, the wavelength sector, that is the monochromator. It is not, that is power of the incident light. This is the sample, and this is the light, and then this light is being detected with the help of what? With the help of the detector. Then it is amplified, and then the readout will be there. Is the here? These are actually blocks which are not in this conversion factor. So coming to the next one, that is the source, I think so. Sources of UV visible radiations. Those are what? That is hydrogen and deuterium lamp. So these hydrogen and deuterium lamps, they are giving us the source, that is 60 to 380 nanometer. This is the range which is being evolved from this hydrogen and the deuterium. This is very narrow range. This is what? This is UV, the vacuum UV region. Now, there is the xenon arc lamp. This is giving us the radiations. They are the sources of the UV visible radiation in the region of 250 to 600 nanometer. So this is giving us a visible region only. Okay. Now there is another one, that is the tungsten halogen lamps. These are most widely used. Tungsten halogen lamps, it means that in this lamp they emit our radiation in the region of 240 to 2500 nanometer, quite wide range. This is the UV visible and also near IR region. So these are being used universally. Very often they are used. The after source is, there is sample container. It is also called as the cuvettes. So these cuvettes, these are made of, this container is made up of different materials and different sizes. Virtually all the UV recorded in solution form, not in the solid state, because in the solid we can't see, that is not transparent. So if solid is non-transparent, it is not being used in the UV visible spectrophotometer. It means to convert our sample into the solution form. Benzene, it is a solution to make a solid one. If, for example, copper is the metal, we will convert it into copper salt, and then we have to convert all the samples into the almost every sample into this form for recording the UV visible spectrum. Now, the could be quartz, borosilicate glass, simple glass, plastic. So These are the generally materials which are being used manufacturing of the containers. That is the cell of the UV visible spectrophotometer. Out of these, only quartz is in the full range of, for example, 200 to 700 nanometer, 200 to 700 nanometer region. It means that when we say transparent, even the glass, simple glass is transparent. When we say it means that this is spectroscopic transparency. This is spectroscopically transparent. What it means transparent in spectroscopic transparency means in this region, these radiations, the material of the quartz, molecules of the quartz, they are not absorbing, they are not interacting the electromagnetic radiation in this region, in this wavelength. So we should use those materials which should be not interfering, which should not interacting with the electromagnetic radiation in which we are using it. Okay. Now there could be the glass, simple glass. Simple glass is transparent, but it is absorbing. It is absorbing in the, especially in the UV region. Simple visible region when we are using colored solution. Okay, simple glass and even the plastic cells made of plastic are transparent, but they are transparent only in the visible region because plastic can what? Plastic can interact in that is the poly absorbing the in the region in the UV region. Similarly, glass interacting with the UV region, but they are transparent in the visible region. So they can be used in the. But again, plastic should be used. Plastic that could not be used when we are using organic solvent. If we are using benzene, for example, we are using acetone. So those solvents, the cell wall of the cell of the plastic cell, so they can be corroded. So their transparency will be. We are using organic solvent like chloroform, carbon tetrachloride, acetone. We should not plastic cell. Rather, we should opt for the glass cell when we want to study in the visible. But if we want to study in the UV region, we must use quartz cell, not glass, not plastic, not simple glass, not borosilicate, but we must use quartz glass because it is transparent, spectroscopic transparency in this 200 to 700 nanometer. But when we say that these cuvettes, that is sample container, they have different material, they have different sizes. That is the path length. That is the beam of the radiation which is path cell. So it varies. The cell thickness could be varying from 1.1 to 10 centimeters. Most commonly used path length is 1 centimeter. It could be in the rectangular shape. It could be rectangular shape or it could be a cylindrical shape. Cylindrical shape means just like a test. So a simple test tube could be used if it is made of quartz. If it is made of the glass, we can use it. Okay, but if it is 1 centimeter, okay, if you make it, no problem. It will solve our problem. It will serve our purpose. Now, wavelength selector, that is monochromatic. How? Ideally, the wavelength selector, it should give us a wavelength which should be a single wavelength. Yes, ideally it should be, but in a real life, no wavelength selector up till now is ideal. It is not ideal. We are not getting a single radiation. We are not getting a wavelength single, but we are always observing a band. Band means it's a combination of and one wavelength. But this wave band, it should be narrow as narrowness of this band, so that, for example, if it is a single wavelength, no, it is not possible. A narrow band of 40 to 80 nanometer, and the other system is that is 40 to 50 nanometer. So the 40 to 50 range as compared to 40 to 80 nanometer. So we are going after the narrowness of the band, so that also prefer not only 10 nanometer, but if it is, for example, 40 to 42 nanometer, it will be more as compared to the 40 to 50 or 40 to 80 nanometer. So the bandwidth is responsible, is better giving us, because it will be giving us better, it is better rather than a broad band. Now, this is the wavelength selector. Now, there are mainly two types of the wavelength selector. Number one is the, number two is the monochromatic. So, a few words about these two. What is that? The filter. Filter permits certain bands of the wavelength. That's the bandwidth of about 50 nanometer to pass through it. What is happening in this filter? We are making a colored glasses. We are using strips of the colored glasses. When we say blue colored glass, it means that it is a blue filter. Yellow, it is a yellow filter. If it is a green glass, it is a glass which is allowing to pass through the green light. So that is when we say green light have a not a single wavelength, but it is approximately bandwidth of 50 nanometer. So the simplest kind of the filter is the absorption filter. The most common of this type is the colored glass filters. Okay. Now the colored glass absorb a broad portion of the spectrum and other portion of its color. Yes, complementary color are being there. Now the benefits of this filters, the colored glasses, they are cheaper, they are low cost, and the second thing is they are technically simple. So technically simplicity and the low cost of this filter, they are the advantages. The disadvantages are they are restricted to the visible region. We can't use the UV region because we can't have a filter, a colored region in this, because in glasses they can't be used in the UV region. They can only be used for the visible region, and they are not very good wavelength. We are having a bandwidth of about 50 nanometer, so they are not good wavelength selector and utilized for research. So the reliability of the research will be using this filter as a monochromatic. because when we say when we are using monochromatic, so these filters they are not to allow the passage of a number of radiations to pass through them, so they will be deviating. The results will be the deviation of Beer law. So due to this reason, these filters monochromatic they are not being used, especially in the research for the research purpose. Monochromatic. They are spectral scanning. They have they are used for the spectral scanning, varying wavelength, radiation over a considerable. They have a wide range. They could be visible region. They have different. They are quite expensive. But their bandwidth is quite narrow. They are not simple also. All the monochromatic, they are similar in mechanical construction. Whether it is quartz glass, it could be made of salts, pure salts. The mono construction is the simple. And the essential components of the mono, they are slates, they are mirrors, they are composed of slates, they are composed of slates, gratings, or prisms. Okay, what is happening? It is a simple one. For example, if we are passing light from here, so this is a slate, there is a lamp source, there is a tungsten halogen lamp. The light is emitting here. This is a mirror. It reflects this light to this. And this is a collimator. Collimator mirror, it is a concave one. So the radiation reaching here, and then it is diverting from here to here. Now, grating. Grating are special material in which there are certain grooves. Grooves are suitable, and when light is passing through it, passes on here, and it will be diffracted to different angles. And so this light is converting into different color. For example, this is violet, this is green, yellow, and red, Vibgyo. And this Vibgyo is reaching here. Again, it is again a column, it is reaching to this slate. Now here this is the region. For example, penetrating here. If we move this here, so this red color can only be emitting from exit slate. If we move into another angle, different angle, for example, violet color, and it will be deflecting out of this slate. So we are getting in the sample container. If we are in between the green, so it will be anchored in such a way that only green will be reaching here, and it will be exiting. It will be exit into the sample compartment. So this is a simple a manufacturing of. It is consistent. This is, for example, this is slate. This is mirror. There are the lenses. So in these, all these are in order to create as monochromatic as we can. So this is the simple manufacturing of the what that is the monochromatics. Now, after passing through the cell, after passing through the solution, the next point is detection. Detection of the radiation. What are the detectors? Detectors could be anyone. That is, detector are the devices that indicates the existence of a physical phenomenon, where something is, that is detecting that something is there, something is happening. For example, this detector could be, for example, photographic film that detect the electromagnetic radiation. Yes, when the electromagnetic radiation they passes on to the photographic plate or film, it gives us the image. Another detector, you are familiar with that, mercury level thermometer for detecting the human body temperature. So that is mercury thermometer that give us the temperature of the body. That is the detector. That is detector. Similarly, the human eye, it is converts the visible radiation into electrical signal to the brain via neurons and gives through the optic nerve, and they give us a signal that something is in front of us. Screen is there in front of us, and that screen showing that we are at the moment we are studying the slide of detector. So this is the naturally made signal and detector. Now, in the instrumentations, in the electronic instruments, that is being used transducer. Those detectors they are being named transducer. So these transducer they are special type of the materials. They are special type of detectors. These detectors they convert the signals. They convert the signals such as light intensity, such as pH, such as mass, such as temperature. So all this light intensity, pH, mass, temperature, they are converted into what? Into electrical signal. And that electrical signal can be subsequently amplified, then manipulated and many times, and finally converted into numbers representative of the original. So, for example, if a light intensity is there, a very light, diffuse light is there. If it is bombarded on this, it is reaching to the transducer. It will give us, for example, some electrons are being emitted. So these electrons are being measured. It is amplified and then they are converted to number, for example, 100 unit, 100 electrons. And that 100 are responsible, for example, radiation of, for example, radiant of power of 50. Similarly, for example, another detector is, for example, change in pH. So what is happening? That is pH. We are reading. We are taking the reading that its pH is 1, its pH is 5, its pH is 14. Okay. Now, but in the beaker there is an electrode, and that electrode is having potential of what? Potential of the hydrogen ion concentration, which is being compared in the hydrogen ion concentration of the electrode. And that electrode, that potential difference is being transferred to the detector. And that change in the potential at the surface of the electrode, and that is being amplified and then is converted into number. That is 1, 2, 3, 4, 14. 14. Similarly, temperature, it is being temperature sensitive materials are there, converting into number. That is the body temperature of a person is, for example, 50 degree. Sorry, not too much, and 35, 34, 39. So this giving us the signal. So these are transducers. So transducers are special materials, special which convert the signal such as light intensity, pH, mass, temperature into electrical signal, which are subsequently amplified and then they converted into number, and they are giving us whether it is high, it is low, it is in between, it is standard, it is up to standard, it is not up to standard. So this is directly proportional to what to the original signal. Okay. Detector and now users, they they are not good. So the what are the requirements? The requirements should be that transducer should have a fast response to low level of radiant energy over a rate of wavelength, wide range of wavelength. It means that this transducer it should have a fast response at, for example, at 200 nanometer, at 300 nanometer, at 700 nanometer. So it should have a fast response to a wide range of the wavelength. It should have a response at 2000 nanometer. So it should have a wide range. So it should be. It doesn't mean that this a transducer. It is being used for 1 500, and then we have to change. No, that should have a wide range. Response should be for the wide range of wavelength. Now, the electrical signal produced by the transducer should be has low noise. So that should be differentiated from the noise value. So it should have a accuracy for with respect to accuracy. It should be accurate. Low noise should be there. And number three, the electrical signal produced by the transducer must be directly proportional to the beam power. It should have a linear response. For example, if the radiation bombarded on the transducer is lesser, so it should give a this lesser signal. If it is greater, it should have a greater signal accordingly. Now, there are different types of transducer which are being used in what? In the UV visible. Two types, mainly two types. The one response that is the photon, that is phototubes. And secondly, the second response is thermocouple, and they respond to the heat. If it is heat is greater, lesser, temperature is greater or lesser, it is being measured by means of what? Thermocouple or bolometer. So these are the two mainly the photons. The one transducer is responsible to measure the photon, measure the heat changes. And for heat changes, what we are using couple and the bolometer. Whereas for the photon measurement, there we are using phototubes generally. And for the photon detector, phototubes are there, photomultiplier tubes are there, silicon diodes are there. So we will be restricting our discussion up to the first two only, rather only one. Yes, because both are they are related with each other. Okay. What is phototube? It is. It is also known as photoemissive cells. Photoemissive cells. This is the photoemissive cell. Glass bulb. Okay. The concave surface of the cathode, which is of concave surface, and this surface is coated with a material, with a thin layer of photoemissive material. Photoemissive material are those material when some light is being bombarded, they give us electrons. They allow electron emitting surface are there. So this cathode with a very thin of photoemissive material, and those photoemissive materials are cesium oxide and silver oxide. If cesium is not available, and silver oxide. These are coated with these cathodes are they're coated with what? These photoemissive materials such as potassium oxide and silver oxide. When the incident light is passing on it, they will emit electrons when they are illuminated with these incident light. And this is a cathode, and this is another anode. Anode and cathode, they are externally connected to a battery. Okay, and when light is it, it is emitting electrons. These electrons, they will run toward the when they are reaching at the anode, and they will be transferred and they will be moved externally toward the cathode. And if, for example, in between there, in we have a galvanometer, we are able to calculate the voltage. We are able to calculate the potential, and this potential is generating this current is directly the number of incident light which are being illuminated on this surface, not a fixed. Simple. This anode is made of what? It is a sheet again. It could be a sheet. It could be a ring. It could be a rod. Whatever it is. It is maintained at high voltage by means of a battery externally. The interior of the bulb may be now this interior of the bulb that is being evacuated, or there could be some inert at very low pressure that is up to maximum up to 0.2 millimeter of mercury. Because if it is not a vacuum is not there, low pressure is not there, the ordinary air is non-conductor. It will not allow the electron to move from this cathode to this anode, and that's all. So this is what this is known as photoemissive cell or simply phototubes. Simple. Okay. Now these when these photoemissive tubes they are being because the number of electrons being emitted from this surface, they are directly proportional to the incident light. So if, for example, one photon is being bombarded, suppose one photon, it is bombarded, it is giving us one electron. And when this electron is bombarded in another cathode, it is electron. And if we are making a series of these phototubes all together, we are getting photo multiply tube, and that is again we arrive at. This is photomultiply tube is a very sensitive device in which electron emitted from the photosensitive surface cathode, it strikes to a second surface called dynode, which is positive to the original cathode. Simple. I am repeating it. This is a photo. For example, this radiation is being bombarded on this surface. This is the cathode. Again, which is cathode. This giving us electrons. When this electron is emitting here, there is another cathode which has high potential as compared to this one. So these electrons, they will be running toward this with high speed. And when this striking is the surface, it has the same coating, and it will giving us two further electrons here. high speed. When these electrons are being generated, there is another third one, that is what? That is another cathode which has a greater potential as compared to this. So they will be running with very high speed toward this. So these two electrons, when they are striking with high speed, they are again giving us four electrons. 1, 2, 3, 4. A multiple component, and these cathodes, they are known as diodes. But these are quite expensive. Sensitivity. So this is generally used in the instruments. Now there could be these, there could be instrument with respect to the arrangement. So I think probably the next slide will be clear. So this is a double beam instrument. The same thing we have arranged according filter. There is a shutter. And from this is a special shutter. It can separate this radiation into two components, and they are passing through different path lengths. One is passing through the reference cell, where the blank solution is present, and the other is passing through the sample cell. The reference cell contains all those materials, all those reagents which are being used in the, but there is no any analyte. But this is containing the analyte plus all other material which are present in this reference cell. So this is the, you can say whatever the reading of this will be, it will be reaching to the detector. So after this reference passing cell, passing the reference cell, there is a detector, photo detector. Similarly, after passing the sample cell, it is a photo detector. And both these are detected, they are differentiated in the amplifier, and then it going to the read. But only this sample beam is present. This portion is not there. So that the single beam instrument is source, filter, sample cell, detector, amplifier, and that of the readout. Only one stabilizer is required for monochromatic. But the light is separated into two words, into reference and beam turn, and it needs two detectors. Two detectors. So electronics measure is ratio. So that will be reading will be there, and then there will be there, and it will be having a ratio of this, which are being differentiated here, and it is being shown in the detector. But the requirement is we must have a required equalized voltage supply. Always a very small change in the voltage, it can no, this is the same. This I was saying that it will be. This is a light monochromator, and there is a mixture. So it is converting into sample and the reference, and then they are again combining to a separator, and then detector, and to amplifier, and to the readout. Okay, the rest is the same thing. Now, the merit of the double beam instrument is it compensates all but most of the short-term fluctuation. So, whatever the short-term fluctuations are there within this, they are being compensated in the double beam instrument. They compensate the drift of the transducer as well as, so if there are certain drifts occasionally, they can be compensated with the help of this double beam instrument. And this is a better design, the double beam instrument better design for continuous recording the spectra. If we are going to record the spectra for a longer period of time, it does. How we can measure the practically? We can measure the practical, we can use the practical. We will make a very dilute solution. For example, maximum amount of the sample is dissolved in what, in 100 ml. A portion centimeter quartz cell or silica cell. The reference cell containing the pure solvent in place. Lambda max is located. We measure the absorbance reading and the absorbance reading of the standards. We plot a calibration curve. Then plot of the absorption of the unknown is recorded, and then they are plotting into the plot. And then from that we can calculate the concentration of the unknown sample. This is the same we have already discussed in various times. Okay, this I included in order to uh, complete the picture. Applications. They are being used in hospitals, for example, for drug analysis, in petrochemical industry, in food industry, in water quality control laboratories, in chemical and biological plants, forensic labs, in chemistry laboratory for the identification of what? Identification of the inorganic organic species, for determination of the structure. So UV visible spectra, along with other data, provides structure information with respect to the bands and intensity of various functional groups. From the bands which are of the wavelength and the intensity, we are able to determine the functional group of a material. Especially for example, when you are going to you are going to synthesize a new compound. So this first for that, this is the basic raw data is must for the identification. We can study the chemical kinetics with the help of this UV visible spectrophotometer. The chemical reaction can be characterized by the disappearance of a functional group. For example, when we are using we are making the, for example, we are going to study the oxidation of an alcohol. So alcohol group has a lambda max. So its intensity, with the passage of time, the oxidation of the alcohol is taking place, and the alcohol will be decreasing, and the oxidized product, that the carboxylic acid, is being presented. So the disappearance of the alcohol group or the band will be decreasing, and the appearance of a new band of carboxylic acid is being uh, emerging with the passage of time. So by this we can calculate the decrease in the concentration of alcohol and the increase in the concentration of carboxylic acid. So we can study the chemical kinetics. We can study isomerism. Isomerism, when a compound exhibits geometric isomerism, such as trans isomer, shows absorbance at higher wavelength and will with larger value of epsilon as compared to the cis isomer. So we can study the cis and trans isomer with respect to with the using this technique. We can also distinguish detection of the conjugation. With the UV visible spectrum, we can establish the presence of the conjugation system in a compound, whether it is double single bond or not. We can use qualitative analysis. UV visible can be used for the qualitative analysis using the lambda max. Lambda means that is the wavelength where the lambda, because every compound, every species, they have their own lambda max. Copper, nickel, cobalt, manganese. So all these elements, they have their own lambda max. Whereas, so we can use qualitative analysis with this. But We can also we can use quantitative analysis. So quantitative analysis, we use number based law calibration curve. We have already explained it in the same lecture, some previous slide. Is there any question? टेस्ट और असाइनमेंट का अगेन बता दें. अच्छा जी, नेक्स्ट वीक जो है, जो आपको असाइनमेंट मिले है, उसकी पहली लाइन के ऊपर लिखा है असाइनमेंट नंबर 1. उसके बाद ड्यू डेट है 4 जनवरी. 4 जनवरी को आपने ये जमा करानी है. कहाँ पे जमा करानी है? आपने इसकी पीडीएफ बना के हैंड रिटन लिखना है. पीडीएफ बना के तो आप पेज के नीचली आखिरी लाइन पे लिखा हुआ है. उसके दिन 4 एक अदर रिटन टेस्ट होगा, 1:30 बजे. 1:30 बजे जब आप आएंगे आपका टेस्ट होगा, और उसके बाद बाकी रिमेनिंग क्लास होगी. दूसरी बात यह है कि इसका जो सिलेबस है जो हमने पहला जो टेस्ट उसके बाद से लेके अब आज तक जो पढ़ा है वो आज के नेक्स्ट एक्सचेंजर्स आयन एक्सचेंज क्रोमेटोग्राफी, आयन एक्सचेंज क्रोमेटोग्राफी से लेके यूवी विजिबल स्पेक्ट्रोस्कोपिक होगा. और ये टेस्ट होगा आपका 4 जनवरी को दिन के 1. करनी आपने जो असाइनमेंट करनी है वो आपने टाइप नहीं करना, आपने हैंड रिटन करना है और उसको इमेज दे के उसको पीडीएफ में कन्वर्ट करके मुझे ईमेल करना है. 4 जनवरी लास्ट क्लास है या नहीं, ये बात की बात है. वो इसलिए कि अभी तो अगर कोई नया प्रोग्राम यूनिवर्सिटी से अनाउंस हो गया तो उसके बाद देखेंगे. लेकिन 4 जनवरी को आपने टेस्ट में अपीयर होना है, तो आपके नंबर लग जाएंगे. नहीं होंगे तो आपकी बात, अपनी मर्जी है. ठीक है जी. एनी अदर क्वेश्चन? एनी अदर क्वेश्चन? टेस्ट रिटर्न ही होता है, ओरल टेस्ट कभी नहीं होता. बड़ा इंटरेस्टिंग क्वेश्चन है. شاید آپ کو کیا سمجھ نہیں آ رہی، اور اسائنمنٹ کے بارے میں آپ کو کیا چاہیے؟ آئین چینج کرومیٹوگرافی سے لے کے آن ورڈ آج تک جو پڑھا ہے وہ سارا ٹیسٹ میں ہوگا. آپ فور کو ہی آپ جمع کرا سکتی ہیں، اس سے پہلے کرانا چاہیں تو اسائنمنٹ جمع کرانے میں کوئی حرج نہیں ہے، لیکن 4 کے بعد اگر نہیں ملے گی تو پھر نمبر نہیں لگیں گے. جی. Any other question? No question? Thank you very much. So for today, it's okay. اللہ حافظ. اگر کوئی کوشچن ہے تو پوچھ لیں. نو کوئی کوشچن نہیں. تھینک اوکے. اللہ حافظ.